In this video, we shall discuss on the characteristic function of a random variable. We shall also find the expectation and variance of the characteristic function of the Poisson distribution. So for more on this topic, you can subscribe to this channel. The first thing to write is the characteristic function of the Poisson distribution, which is exponential lambda exponential it minus lambda. So this is the imaginary unit, this I here, or the characteristic function. Now, to obtain the expected value of x, we first obtain the expected value of x. The expected value of x will be the first derivative of the characteristic function. So for we to differentiate this, we need to employ what is called the function of a function method of differentiation. So that is what we use in differentiating this, which implies that we use something like this: the y all over the t is equal to the y all over the t multiplied by the u, the y all over the u multiplied by the u all over the t. So this is what we use. Now, we say let u be equal to the whole of this function, which is lambda exponential it minus lambda, and y be equal to exponential u. The whole of this is u, so exponential u. So the first thing to do here, meaning our first derivative, which is equal to this, we first find the y all over the u. We'll find the y all over the u. So the y all over the u, the y all over the u. If you differentiate an exponential function, you still get that same function. The y all over the u will give us exponential u. Also, we differentiate the u all over the t. The u all over the t, which is this function. So if we differentiate the whole of this, we'll get lambda. We'll have the imaginary unit exponential it. So this is what we'll get, because this will turn to 0. So it then means that our characteristic function will be equal to, now we note that this implies the y all over the t, which is equal to the y all over the u multiplied by the u all over the t. So here our characteristic function is equal to the y all over the u. The y all over the u is exponential u multiplied by the u all over the t, lambda I exponential it. So this is what we get. Of course, we say, but our u is equal to something. We have our u to be this. So our u is lambda exponential it minus lambda. So it then means that our first derivative is exponential. We put our u, lambda exponential it minus lambda, multiplied by lambda I exponential it. So we now say at t to be equal to 0. At t equal to 0, that means anywhere we see t, we put 0. So we move over to this side of the board. For more on this topic, you need to subscribe to this channel. So anywhere we see t, we put 0. It then means that our characteristics function will be equal to exponential lambda exponential I 0 minus lambda multiplied by lambda I exponential I 0. We say, but from indices, we note that exponential I 0 is equal to exponential 0. And anything raised to the power of 0 is equal to 1. Anything raised to the power of 0 is equal to 1. So it means anywhere we see our exponential function, we turn it to 1. So it then means that at t is equal to 0, you have exponential lambda. This has turned to 1 minus lambda multiplied by lambda I. Now, we also note that this is equal to exponential 0 multiplied by lambda I. So it then means that our characteristics function is equal to lambda I. Now, how do we remove this? We first go to where we write our expected value. Now, we write our expected value this way, here. Expected value of x. So, our expected value of x is equal to negative I is equal to, since we have the whole of this to be lambda I, so we have negative I multiplied by lambda I, which is the same thing as negative I squared multiplied by lambda, which is the same thing as our expected value. We say, but I squared is equal to minus 1. So we have that our expected value of x is equal to negative into negative 1 multiplied by lambda. Therefore, our expected value of x is equal to lambda. So this is our expected value of x, and this is how we can obtain the expected value of x. The next thing to do is to obtain the expected value of x squared. To obtain the expected value of x squared, because this will enable us obtain the variance for the Poisson distribution. So to obtain this, we will first recall what we got from our first derivative. So we recall that for our first derivative, we got exponential lambda EIT minus lambda multiplied by lambda I EIT. So to obtain our expected value of x squared, which is the second derivative of our characteristics function. Now we take the second derivative of this function. That means we employ the product rule of differentiation. So we move over to this other side. For more on this topic, you need to subscribe to this channel. Now, for To obtain our expected value of x, we find the second derivative, which implies that we have u dv all over dt plus v du all over dt, because we'll be differentiating with respect to t. Now, the whole of this function becomes our u, while the whole of this function becomes our v. So, our characteristics function for the second derivative will be equal to u. U is the whole of this function, so we have u to be exponential lambda eit minus lambda multiplied by the v all over the t. So we differentiate this, the v all over the t. We'll have lambda, we'll also have the imaginary part again. So we'll have the imaginary part to be I squared exponential I t plus v. What is our v? V is lambda I e I t. V is lambda I e I t multiplied by the u all over the t. So we differentiate this, the u all over the t. The u all over the t will give us exponential lambda e I t minus lambda multiplied by what is inside here, lambda I e I t. So if we differentiate this function, we get the whole of this. If we differentiate this function, we get the whole of this. So that is it. The next thing we do, we say at t is equal to 0. It then means that our characteristics function at t is equal to 0 is equal to, anywhere we see t, we put 0. So we have that our exponential value, lambda p I 0 minus lambda multiplied by lambda I squared p I 0 plus lambda I p I 0 multiplied by exponential lambda p I 0 minus lambda multiplied by lambda I p I 0. So anywhere we see 0 and t, we put 0. So we note that exponential, we say, but from indices, exponential I 0 is the same thing as exponential 0, which is also equal to 1. Because anything raised to the power of 0 is 1. So anywhere we see our exponential function, we put what? 1 there. So we move over to the other side of the board to compute. We move over to this side. We should not also forget that our expected value of x is lambda, because we recall that when we are looking for the variance. For more on this topic, you need to subscribe to this channel. So it then means that our second derivative for our characteristics function is equal to exponential lambda minus lambda, because this has come to 1, multiplied by lambda I squared, this is also 1, plus lambda I, this is also 1, multiplied by exponential, this is 1. So we have lambda minus lambda multiplied by lambda I, that is 1. So we have exponential 0 lambda I squared plus lambda I exponential this minus this is 0 multiplied by lambda I. So we say but exponential 0 is equal to 1. So we have that our characteristic function for the second derivative is equal to lambda I squared plus this multiplied by this will give us lambda squared I squared. Of course, we note that since we have I squared common, we can bring it out, which is I squared to be lambda plus lambda squared. It then means that we can now write our expected value of x squared, which is equal to negative I squared, our characteristic function, to be equal to, because of this I negative sign, we put it here, we have negative I squared into lambda plus lambda squared. So how do we compute this? We recall that we say but I squared is equal to 1. It then means that our expected value of x squared is equal to negative into negative 1 into lambda plus lambda squared. So that is what we'll get. Now, negative sign will cancel negative sign to give us 1. So we move over to this side to write our expected value of x squared. For more on this topic, you need to subscribe to this channel. So we are to write our expected value of x squared. So we have the expected value of x squared will now be equal to lambda plus lambda squared. So it then means that this is our value for the expected value of x squared. We should also note that we have the expected value of x to also be lambda. So this is what we have succeeded in getting for the expectation of the characteristics function of the Poisson distribution. The next thing to do is to look for the variance. So we'll now look for the variance for the characteristics function of our Poisson distribution. So we move over to the other side of the board. For more on this topic, you need to subscribe to this channel. So we know that our variance of x is equal to the expected value of x squared minus the expected value of x all squared. So we can recall that we got for the expected value of x squared, we got lambda plus lambda squared, which is this, and for the expected value of x, we got lambda. We got lambda. All we need to do is just to substitute what we got for the expected value of x squared and the expected value of x. So for the expected value of x squared, we got lambda plus lambda squared minus the expected value of x is lambda. all squared. So our variance will now be lambda plus lambda squared minus lambda squared. So this is what we got. Of course, this can cancel this. So it then means that our variance of x is equal to lambda. So we have succeeded in finding the expectation and variance for the Poisson distribution. For the expected value of x, we got this. For the expected value of x squared, we got this. And for the variance of x, we got lambda. For the characteristics function of Poisson distribution. For more on this topic, you need to subscribe to this channel.